Good morning, friends. Up to our discussion, we discussed more than 30 numerical asked in competitive exam of ray optics. Now, today we consider the more numerical MCQ type question asked. Now, listen here: the two identical glass equiconvex lens of effective index 3/2 of focal length f, each are kept in contact. The space between the two lenses is filled with water, having the effective index 4/3. The focal length of combination is, that is asked in 2016. Now listen, here the one mistake is in this numerical is that here the two lenses having the focal length f is given. Instead of this, suppose there is given the two identical glass equiconvex lens of radius of curvature r is given. So at that time, how we can find out the focal length of combination? For that purpose, first video and this type of the numerical already we discussed earlier. At that time, the two convex lenses are placed in contact with each other, and the space between these two lenses is filled with a oil, and we find out the focal length of combination. Okay. For that purpose here, the combination of these two lenses is like this way. There is the lens 1, there is lens 3. Now the space between them is filled by water. So that is that there is second lens having the focal length is f2. Here the focal length of first lens is f1, and for second lens this lens is f3. We have to find out the focal length of these three lenses, and using the equation of the focal length of the combination, 1 upon f is equal to 1 upon f1 plus 1 upon f2 plus 1 upon f3. For that purpose, to find out the focal length, here already given f1 is equal to f3, because both are identical, is equal to f. Instead of given directly f, if the radius of curvature of both equiconvex lenses are same, that means the r. At that time, how we find out? For that purpose, from lens maker's formula, one upon f is equal to n minus 1 into 1 upon I1 minus 1 upon I2. For lens 1 and 3, lens 1 and 3. First we find out the focal length. 1 upon f1 is same as the 1 upon f3 is equal to mg minus 1 upon I1 minus 1 upon I2. Here I1 is equal to r, I2 is equal to minus r, and I we consider as f. I is equal to f. Therefore, 1 upon f1 minus 1 upon f3 is equal to mu z, already given 3/2 minus 1, here 2 by r. 3/2 minus 1, so that means the 1/2 into 2 by r, that means the 1 upon r is equal to 1 upon f. Therefore, f1 is equal to f3 is equal to f. Now, for a concave lens of water, so focal length is 1 upon f2. Here the nw minus 1 upon I1 minus 1 upon I2. For this concave lens, I1 is equal to minus R, I2 is equal to R. Now we substitute the value. That is for water, 4 by 3 is given. 4 by 3 minus 1. Here minus 2 upon r. Minus 2 upon r. As we simplify it, we obtain 1 upon F2 is equal to minus 2 upon 3R is equal to minus 2 upon 3F. Therefore, resultant 1 upon F is equal to 1 upon F1 plus 1 upon F2 plus 1 upon F3. Therefore, F is equal to 4F by 3. As we simplify, substitute the value and simplify it, we obtain the answer is 4F by 3. So where is the numerical? Only the use of lens-maker's formula. Here for F1 and F2, that means the both convex lens, the focal length are given same, that is the F directly given. Only we have to find out the focal length of what are the space between the two convex lens. This space is concave. And water is present, so that forms the concave lens of water, and we find out this focal length. Okay. Now next is an air bubble in a glass slab with the effective index 1.5. Near normal incidence is 5 cm deep when viewed from the one surface, and 3 cm deep when viewed from opposite face. The thickness of the slab is. Now listen, first we do the diagram. There is the glass slab. There is the AB surface and there is the C. Yes, we are observing this air bubble. Air bubble is here. That is the real depth. Here we are observing from AB surface. At that time, there is appear at here. So real depth is HO. We obtain at HI. HI is given as the 5 centimeter. One from the 5 centimeter. Now, as this air bubble is observed from other side, from this side, there is the real depth. So there is the HO dash. At that time we obtain it here. There is the HI dash. Apparent depth, that is given the 3 centimeter. That is given as 3 centimeter HI. Now we know that the effective index is equal to the apparent depth upon real depth. Clear this? Therefore, and there is the thickness of a slab. There is the thickness of the slab. Lastly, as we find out the real depth in both cases, HO and HO dash. So, thickness of the slab P is equal to HO plus HO dash is equal to NHI plus NHI dash in common HI plus HI dash. N is given, the effective index of the glass is 1.5. Here 5 plus 3, 8. Therefore 12 centimeter is the answer. 12 centimeter is answer. Now listen. So this numerical is important. Here the glass slab is given, that is the paperweight. In this paperweight here, the air bubble is inside. What is the thickness of this paperweight or this glass plate? As we are observing this air bubble from the downward direction or from one surface, and then the apparent height or the apparent depth is 5 centimeters. Now on opposite surface, that means as we are observing from this side, at that time the apparent depth is 3 centimeters. So what should be the thickness of a glass slab? Thickness of a glass slab is the addition of real depth from one side plus real depth from other surface. So T is equal to HO plus H on S. Now we are using N is equal to HI upon HO. N is equal to HO upon HI. Therefore HO is equal to N H. N is common, HI plus HI dash. So 1.5 plus 5.3 is equal to 12 centimeter is our answer. Right? Okay. That is equal to 12 centimeter. Now listen, next. If the angle of prism is 60 and angle of minimum deviation is 4, A is given 60, minimum deviation is equal to 4. The angle of refraction is, we have to find out the angle of refraction I1 or the R. For minimum deviation, how we obtain it? So I1 is equal to I2 is equal to I. But we know that A is equal to I1 plus I2, that means the 2I. Therefore I is equal to A by 2. A is given 60 by 2, that means the 30 degree. Here minimum deviation is given, that means whatever the incident ray in a prism, the reflected ray is parallel to the base of a prism. Therefore, the I1 and I2 has the same value for minimum deviation condition. So, minimum deviation condition, and due to that reason, we take the I1 is equal to I2 is equal to R. And using the concept A is equal to I1 plus I2, that means the 2R. Therefore, angle of refraction R is equal to A by 2. A is given 60 degree. So 60 by 2, 30 degree. Here is O. Now next numerical, a coin is at rest at the bottom of a tank filled with a liquid. A ray of light coming towards the surface will move on surface after incident on it. Then what is the speed of light in a liquid? Now listen, for this numerical figure is given, and the figure is like this way. There is the tank filled with a liquid, and there is the upper surface. Here a coin is placed here. Now the ray coming from the coin is incident on the surface this way. There is the normal due at this point of incidence. So there is the angle of incidence I. There is the angle of incidence I. Now after the refraction, this ray goes parallel to the surface. Parallel to the surface. Now here this value is given, there is the 4. And this distance is given the 3 centimeter distance. So in that case, we have to find out what is the speed of light. Now listen, here the incident ray suffers the total internal reflection. Here I is equal to C, critical angle. Here I is equal to C. Therefore, sin C is equal to 1 upon N. Sin C is equal to 1 upon N. Therefore, N is equal to 1 upon sin C for the sin I. And from figure, if we consider this right angle triangle, so this angle is I, so that is also I. Sin I, 3 upon 4, 3 upon 5. sin C is equal to 3 upon 5. Therefore, n is equal to 1 upon 3 by 5. Therefore, 5 by. Now, we know that n is equal to C by V. Therefore, V is equal to C by N. C is V is equal to C by N. C is 3 into 10 is to 8. N is 5 by 3. Therefore, 1.8 into 10 is to 8 meter per second is the answer. Again, here the figure is given, the depth of a coin is 4 centimeter and from the one edge is 3. Therefore, here the whatever the ray coming from the coin is after the reflection goes parallel to the surface. Therefore, the eye must be C. And also we have the condition for total internal reflection, sin C is equal to 1 upon N. Therefore, N is equal to 1 upon sin C. And from figure, sin C is equal to opposite to the hypotenuse. Therefore, N is equal to 1 by 3 by 1 upon 3 by 5 is equal to 5 by 3. Now, refractive index N is equal to C by V. Therefore, V is equal to C by N. We substitute the value. So, our answer is 1.8 into 10 is to 8 meter per second. Clear? Okay. Now the next numerical, the diameter of the objective of a telescope is 10 centimeters is given. Its distance from the two different objects is 1 kilometer. If the wavelength of a light is 5,000 angstrom, then at what minimum distance these objects are clearly seen by the telescope? Now what is given? The diameter of a telescope is given. Right? And that is given as the 10 centimeter. And the distance from the two different objects is 1 kilometer. Is 1 kilometer. Okay. Wavelength is given 5,000 angstrom. 5,000 angstrom. Therefore, 5 into 10 is to minus 7 meter. Right? Distance is given 1 kilometer distance. D is equal to diameter. Diameter is given the 10 centimeter. 10 centimeter, that means the 0.1 meter. 0.1 meter. Okay. Now we have to find out at what distance we obtain its image clearly, minimum distance. So for a telescope, x upon 1000, that means the 1 kilometer is equal to 1.22 lambda upon v. 1.22 lambda upon v. Therefore, x, what is the x? X is the minimum distance these objects are clearly obtained, seen clearly. Okay, therefore, x is equal to 1000 into 1.22 lambda upon v. Now 1010 is to 3, 1.22 into lambda, 5 into 10 is to minus 7 upon d, that means the 0.1. So we obtain the value is 6.1 millimeter. 6.1 millimeter is in order of 5 millimeter, which is order of 5 millimeter. Order of 5 millimeter. Therefore, answer is 5 millimeter. Now, keep in mind that for a telescope, x upon 100, right? That means the ratio of the distance between the two objects to the distance. Actually, that's the angular dispersion, right? So is equal to 1.22 lambda upon capital B. So here x is equal to 1000 into 1.22 lambda upon capital B. We substitute the value, we obtain the answer 6.1 millimeter. Now, no any answer, only the D option is given in millimeter. So our answer is 5 millimeter. Because the order of the separation between the two images seen clearly is in order of millimeter. Because our answer is 6.1 millimeter, therefore answer is 5 millimeter. Now next, a microscope is used to observe a mark on a piece of a paper clearly. Now, if a cube of a paper index 1.5, that means the glass cube is placed on this mark, and thickness 3 cm is placed on this mark. Then, now what should be the displacement given to a microscope to observe the mark clearly again? Now what it says that? Here the one mark is given on this paper. This mark is supposed to be. That is observed by the microscope. Now, one glass slab is placed on this paper, glass paper. To focus this P.S. One glass slab is placed this manner. So we have to move upward. This microscope, there is the X, we have to find out this value. First microscope is focused at T. First microscope is focused at P, and then focused at P dash, at P. Therefore, apparent depth or to shift the microscope or move the microscope up is equal to real depth minus apparent depth. Actually, there is not apparent depth. The shifting of a microscope, or the displacement of a microscope, is equal to real depth minus apparent depth. Therefore, real depth is 3 minus 3 upon 1.5. 3 upon 1.5. Therefore, 3 minus 2 is equal to 1 centimeter. We have to move upward. 1 centimeter moves upward. Actually, this type of the practical you have the in syllabus. We have to find out the effective index of a glass slab. At the time, first we are observing the line mark on a paper by a simple microscope directly. After that, we need to place the glass slab. To focus the image of this line, we have to move up the microscope. So, what is the displacement of this microscope? Okay. After that, the third part in experiment is that we place the dust powder on a glass slab and again try to focus the line. So again we need to move up the microscope. So here, first the microscope is focused at P and then at P'. Therefore, the displacement of the microscope is equal to real depth. That is the real depth. Minus apparent depth. Therefore, 3 minus 3 upon 1.5. So 3 minus 2, that means the 1 centimeter. So 1 centimeter moves upward. Now, for which light, the focal length of a convex lens is maximum. Right? A light with the minimum frequency undergoes the total internal reflection. A light with minimum frequency undergoes total internal undergoes the minimum deviation. Undergoes minimum deviation. Now, a red light has frequency is minimum. A light has the frequency is minimum. So that the focal length of a given lens for red light is maximum. Again, the light with the minimum frequency undergoes the minimum deviation. Red light has the minimum frequency. Therefore, the red light undergoes the minimum deviation. Therefore, the focal length of the lens for the red light is maximum. Okay, now the next numerical, as shown in figure, a ray of light is incident on a glass slab. If it experiences the total internal reflection in vertical plane, then what is the effective index of a glass? Right. First, we are applying the Snell's law at point A, 8.8. From Snell's law, effective index of a glass with respect to the air, that means the NGA, is equal to sin 45 upon sin r. Right? Therefore, 1 upon root 2 sin r. Therefore, sin r is equal to 1 upon root 2 NGE. There is the equation 1. For point B, at point B. The same way, sin 90 minus r is equal to NAG, effective index of a medium with the glass. Right? So is equal to 1 upon NG. 1 upon NG. And cos 90 minus sin 90 minus r, there is a cos r, is equal to 1 upon NG. Therefore, NGA is equal to 1 upon cos r, is equal to 1 upon under root of 1 minus sin square r. Making the square, therefore NAG square, substitute here, NAG square is equal to 1 upon 1 minus sin square r, therefore 1 upon 2 NGA square. Therefore, we can take the LCM 2 NGA square upon 2 by 2 NGS square minus 1 is equal to NAZ. And NGE. Effective index of glass with respect to the air. So 1 times there is cancel. Therefore, 2NG square minus 1 is equal to 2. Therefore, NGS square is equal to 3. Therefore, NGE is equal to root 3 by 2. Therefore, effective index of a glass slab with respect to the air medium is root 3 by 2. Again, first we apply the scales to N1 sin I is equal to N2 sin I. Therefore, N is equal to 1. Here that is the NG. Here is therefore the NG sin 45 on sin I, sin 45 1 upon root 2 sin I. Therefore, sin I is equal to 1 upon root 2 NG. Or the simply NG. Now, simply at point B, the rays undergoes the total internal reflection. Therefore, same way we can add from this equation sin 90 minus R is equal to NAZ. So as we take in denominator, so there is the NGE. Take the NGA, there is the cos R, 1 upon NGA. Take the NGA here, cos R here, and convert the cos into the sine. And simplify it, we obtain the NGA is equal to root 3 by 2.